Hello everyone, my name is Kesh Nitya. Today I am going to discuss about understanding the Hilbert transform, definition, explanation and comparison and application. What is Hilbert transform? It is a mathematical operator, a linear operator that transforms a real valued function u of t into another function h of u of t. The Cauchy principal value is defined by convolution with ensuring integrability. Here h of u of t is equal to 1 by pi integral minus infinity to infinity u of t by t minus t dt. 90%, 90 degrees phase shift. Crucially, it introduces at plus or minus 90 degrees phase shift to every frequency component of the signal. This unique property makes the Hilbert transform indispensable for signal analysis, particularly in creating analytical signals. In intuition behind the Hilbert transform, real to quadrature. In transforms, it transforms a real signal into its quadrature or imaginary counterpart, fundamental for complex signal representation. Analytic signal construction forms an analytical signal z of t is equal to u of t plus I into h of u of t, enabling direct extraction of instantaneous amplitude and phase. Frequency domain effect acts as a filter, shifting all positive frequency components by minus pi by 2 and negative frequency by plus pi by 2. This time domain operation provides a unique lens for understanding complex signal characteristics that are otherwise difficult to ascertain from the real signal alone. Here the differences between Hilbert transform and Fourier transform. Key differences. Fourier transform converts signal from time domain to frequency domain, reveals the global amplitude and phase spectrum, decomposes signals into constituent sinusoids, requires signals to be stationary for accurate spectrum interruption. Here the Hilbert transform operates primarily in the time domain, creates a 90 degrees phase shifted version of the original signal, use it to form analytical signals for modulation analysis. A singular integral operator less sensitive to stationary for certain applications. While both are integral transforms, they serve distinct purposes in signal analysis, with HT focusing on instantaneous properties within the time domain. Here the mathematical relationship between Hilbert transform and Fourier transform. The two transforms are Here, the two transforms are intricately linked through the frequency domain representation, revealing how HT modifies the signal spectral components. Frequency domain operation. The Fourier transforms of the Hilbert transform of u of t is given by f of h of u of is enclosed between brackets omega is equal to minus I sigma of omega f of u of omega, where omega is the sine function indicating how positive and negative frequencies are treated. Double application property. Applying the Hilbert transform twice effectively reverses the phase shift resulting in the negative of the original function. h of u is equal to minus u. This property highlights its characteristic phase shifting behavior. Applications of Hilbert transform. Applications of Hilbert transform: signal processing, communications, acoustics, vibration analysis. In signal processing, used in envelope detection, instantaneous frequency estimation, and creating analytic signals for complex demodulation. In communications, essential for analyzing amplitude modulation and frequency modulation signals, especially for demodulation. Biomedical engineering applied in physiological signal analysis for tasks like latency analysis and phase synchronologistics in EEG and ECG data. In acoustics, benefits include speech data compression, signal processing for adultery processes, and sound analysis. Vibration analysis, crucial for nonlinear system diagnostics, fault detection in machinery, and model analysis in mechanical engineering. The Hilbert transform ability to reveal instantaneous signal characteristics makes it invaluable across diverse scientific and engineering disciplines. Visualizing the Hilbert transform effect. Imagine an original real valued signal such as cosine wave. The Hilbert transform produces its quadratic counterpart, a sine wave, phase shifted by exactly 90 degrees. At left, original real valued signal, example cos omega t. Hilbert transform output at right side, sin omega t, showing the precise 90 degrees phase shift. These two components together form an analytical signal, enabling a clear representation of instantaneous amplitude and phase modulation as depicted in the visual. Simple example problem. Hilbert transform of cos of omega t. Let's consider a fundamental signal to illustrate the Hilbert transform effect. Here the original signal is given a real valued cosine function u of t is equal to cos omega t. Hilbert transform result. The Hilbert transform of u of t is simply a sine function. H of u of t is equal to sine omega t. Analytic signal. Combining these two yields the analytic signal, a complex exponential. Z of t is equal to cos of omega t plus ij sin omega t is equal to e plus j omega t. This example elegantly demonstrates how the H2 generates the imaginary component needed to construct a complete complex exponential form a real sinusoidal. Step-by-step computation of the example. Here original begin with the signal u of t is equal to cos omega t. Here Fourier transform. The Fourier transform of mathematical of u consists of impulse Dirac delta function located at omega in the frequency domain multiplied by minus I text signum or omega. In the frequency domain, multiply the positive frequency component by minus I and the negative frequency component by plus I. Inverse Fourier transform. Perform the inverse Fourier transform of the modified frequency spectrum. To obtain sin omega t, construct analytical signal. Combine the original signal with its Hilbert transform to form the analytical signal. Z of t is equal to e power I omega t. Here the summary and takeaway. Powerful tools of the Hilbert transform. The Hilbert transform creates analytical signals by phase shifting components by 90 degrees, offering profound insights into signal characteristics. Complementary to Fourier transform. It complements the Fourier transform by enabling time domain complex signal analysis, focusing on instantaneous properties. Diverse applications. The widely used applications in Hilbert transforms in communication, biomedical signal processing, and vibration analysis for advanced diagnostics and analysis we have studied before. Deeper insights. Understanding Hilbert transform depends insight into signal phase, amplitude, and instantaneous frequency, crucial for modern engineering. Further exploration. Applying Hilbert transform to real-world signals reveals envelope and phase behavior and enhancing practical signal interruption. These are the concept about Hilbert transform and clear explanation. Thank you.